Hello, everyone. Today, we'll be talking about how to allocate and free fixed-size memory blocks in a concurrent setting with asynchronous processes. Memory allocation is a fundamental problem that's used by many lock-free and wait-free data structures. Although some data structures require variable-sized memory blocks, many are built on fixed-size blocks, including linked lists and trees. In our paper, we focus on the fixed-size memory allocation problem. We'll use M to denote the number of memory blocks we are managing, K to denote the size of each memory block, and P to denote the number of asynchronous processes in our system. Throughout the paper, we assume that K is at least 2 because we store some allocator metadata inside the memory blocks. Our main result is a linearizable implementation of allocate and free with the following properties. First, both operations take constant time, and time is measured by the number of local and shared memory instructions executed by an operation before it completes. The space overhead of our allocator is k times p squared, which means that on top of the m memory blocks that it manages, it also requires k times p squared space for internal data structures. And when we talk about space complexity, we are accounting both local and shared variables. If our allocator is initialized with m memory blocks, then it's able to allocate up to m minus p squared at a time before running out. We are not addressing the problem of supporting an unbounded number of allocated shells. This would seem impossible without some assumption of how the operating system gives out large chunks of memory. Finally, our allocator uses only single word pointer width, read, write, and compare and swap. This means that each base object is just big enough to hold a pointer, and this allows us from hiding bits in pointers or using unbounded sequence numbers. Although this result is mostly meant to be a theoretical contribution, the constants are small, so we believe that it will be fast in practice as well. While there has been significant work on lock-free memory allocation, wait-free memory allocation has gotten relatively little attention. The only wait-free memory allocator we are aware of is by Agazadeh and Wolfel from DISC 2016. The main focus of their paper was not actually on memory allocation, but they implemented a release and get free operation that each takes constant time and can be used for fixed-sized, allocate, and free. However, their algorithm requires p cubed space per memory block, which is too much in many applications. So the contribution of our work is that it gets the same time complexity, but with much less space overhead. Our work complements a large body of existing work on concurrent memory reclamation. The memory reclamation problem is about determining when a block is safe to free, whereas the memory allocation problem is about determining how to allocate and free memory blocks. In the interest of preserving the progress guarantees of wait-free data structures, there has been recent progress in designing fast, wait-free memory reclamation techniques. For example, there was a paper in PPOP this year where Nikolov and Ravindra presented a wait-free version of hazard errors, and they show this algorithm to be very fast in practice. With the introduction of wait-free memory reclamation, the memory allocation part becomes a new bottleneck, so making memory allocation wait-free and fast is very important. Our algorithm is actually very simple. We maintain a private pool of memory blocks for each process, and in the common case, most calls to allocate and free will be handled by these private pools. We also maintain a shared memory pool, which is used to load balance the private pools in case one gets too full or too empty. This general idea has been widely used in concurrent memory allocators, and it has been shown to be fast in practice. The specifics of how the private pools and shared pools are implemented differ from algorithm to algorithm. So let's take a look at how our implementation works in more detail. Here's a diagram of how our allocator is structured. I'll use this box symbol to denote a memory block of size k. In our algorithm, blocks are transferred between the private and shared pools at the granularity of batches, which I'll represent using this array. This notation can be a little misleading because the array implies that the batch is contiguous in memory, which is a very common requirement in previous work. But this is not the case in our algorithm. Our batches are actually implemented as a linked list, where each block stores a pointer to the next block in the batch. Also, a full batch in our algorithm contains B blocks, where B is some constant multiple of P. Our shared pool is implemented using a concurrent stack, where each node stores a pointer to a batch. The concurrent stack, we use supports pushing and popping in order of p time, but since we want alloc and free to take worst case constant time, we break up the push and pop operations into p steps, each of which takes constant time. Each call to alloc and free will perform one step towards any ongoing push or pop operation on the shared pool. The private pool actually needs to be carefully managed so that it doesn't contain too many or too few blocks, and also so that there's only one ongoing push or pop operation per process. The problem with holding on to too many blocks is that it leads to high memory overhead, since these blocks cannot be allocated by any other process. There's one last difficulty when managing the private pools. It turns out that the concurrent stack used inside the shared pool also requires dynamic memory allocation for its nodes, which would make the problem seem recursive. We handle this problem by having the shared pool allocate from the same private pools as the user, and we will make sure that the private pools always have enough blocks to serve both the shared pool and the user. Now I'll briefly go over how our private pool is implemented and then as well as the shared pool. So as mentioned before, our shared pool is maintained using a concurrent stack, and this stack is based on the PSIM stack. So PSIM is a universal construction designed by Vituro and Kalamanis, and a universal construction is a general way of transforming any sequential data structure into a concurrent one. The PSIM stack is the result of applying the PSIM universal construction to a standard sequential pointer-based stack. The PSIM stack has a lot of nice properties. It is weight-free, and both push and pop operations take order of p time. However, it doesn't do memory management, so it provides no bounds on space usage. We show how they modify the PSIM stack so that it uses at most m plus p squared space, where m is the size of the stack. Our memory reclamation technique is very lightweight, and it just involves adding a few validate link operations on one of the LLSC objects. So when adding memory management, we also need to bound the amount of times each push or pop operation calls allocate and free. This bound is important because the concurrent stack allocates memory from the private pools, so we need to make sure that the private pools don't become empty or overflow. Finally, we modify the PSIM stack so that it uses only pointer width, read, write, and compare and swap. The original PSIM algorithm doesn't satisfy this property because it uses LLSC, but the recent results show that it's possible to simulate LLSC and constant time using just pointer width, read, write, and cast. So that's an overview of how our shared pool works, and the full details can be found in our paper. Now let's take a look at the private pools more closely. Each process will maintain between 1 and 3B blocks in its private pool, and a process may also have either an ongoing push or pop operation from the shared pool. An allocate begins by removing a block from the private pool, and if there is an ongoing push or pop, then it performs one step towards that operation. If there is no ongoing push or pop, and the number of blocks in the private pool drops below B, then the alloc operation invokes the pop operation from the shared pool. The pop will complete after P calls to either alloc or free, so we need to make sure that the private pool has enough blocks to handle all the allocate operations while it waits for the pop to complete. During this time, there can be P calls to alloc from the user and 2 P calls to alloc from the shared pool. So we need to set the batch size B to be at least 3P to avoid running out of memory blocks. A free operation adds a block to the process's private pool and performs a step towards any ongoing push or pop, just like before. If the number of blocks in the private pool goes above 3B, then it begins pushing a batch to the shared pool. With this protocol, you can show that you will never invoke a shared push operation if there is already an ongoing operation on the shared pool. Together, these two operations ensure that there's always between 1 and 3B blocks in the private pools. In summary, given recent advances in weight-free memory management and weight-free data structures, it's also important to have weight-free memory allocation to preserve these progress guarantees. We solve this problem in a special case where there is a fixed-size memory pool of fixed-size memory blocks. It would be interesting to see how to remove these restrictions while still preserving weight freedom. Our solution is fairly simple. We use the PSM stack with memory management to implement a shared memory pool. Accessing the shared memory pool is expensive, so we add a layer of private memory pools which handle most of the requests. The private memory pools also handle the memory allocation needs of the shared pool. So our solution guarantees worst-case constant time for allocate and free, and this holds even when the processes are arbitrarily slow or even crash. Our allocator requires k times p squared space for internal metadata and is able to allocate all but p squared memory blocks. And finally, it only uses a single word pointer with read, write, and compare and swap, which makes it portable. And that's all for this talk. Thank you for listening.